everyone, and welcome to another PAT Problems video. My name is Helena and I'm the Access and Outreach Manager for the Department of Materials at the University of Oxford, and today we're going to be taking a look at the long question from the 2012 PAT paper. Now, as I mentioned in a previous video, the PAT as it currently stands doesn't have these long questions in its current format. However, they are still good practice. So let's have a look at this question. So here we have a point-like object with mass equals 1 kilogram, which starts from rest at a point x0 equals 10 meters and moves without any friction under a force F. So this force F is the only force, which depends on the coordinate x as illustrated in the figure below. And the motion is confined to one dimension along x. Okay, so we're given this graph which shows this force acting on this object as a function of its x coordinate. Okay, so for the first part of this question, we are being asked to find its speed at x equals 0. Okay, so before we dive into answering the question, let's just take a look at this graph and try to digest a little bit about what it's showing us. So we can clearly see on this graph we have two sort of regions. So here, where x is greater than 0, we have this region where we have a constant force, and this is a value of minus 10 newtons. Okay. And as soon as we get to x is less than 0, we have this linear force here, which increases as x gets more negative, as x decreases. Okay. So this has got me thinking that as we're working through this question, we're probably going to have to split this motion up into these two sections. Okay, so I'm going to label them here, section 1 and section 2, just so we can keep track of what we're talking about. Okay, what is its speed at x equals 0? So at this point here. So we're starting from rest here, and we're moving to x equals 0. So this is all in the region of the constant force. So in this case, we're in region 1, and an equation for our force as a function of x is simply minus 10 newtons. So it's constant. Okay, so what's this telling me? Well, this means that I can work out the work done on this object, which, if we want to do it thoroughly, the energy or the work done would be the integral of f of x dx. But obviously in this case, since it's a constant force, that's equivalent to the force times the distance moved, which I'm just going to call s, and we can equate that to the kinetic energy of the object as it's moving. So in this case, we have a force of, I'll keep the signs in just to keep track of them, of minus 10, and the distance as well is we're moving from 10 to 0, so it's minus 10, and that's equal to half times its mass, which is 1, I'll write it in just to keep track, times its velocity squared. Okay, so if we multiply those out and rearrange it, we have that v squared equals 200, which gives us a speed of the square root of 200, otherwise known as 10 root 2 meters per second. So that's the first part here. So that's working in the easy part of this graph. So what's the next part question asking us? So here we're being asked to sketch its kinetic energy as a function of x. So I've just copied across here the graph that we were given showing the force as a function of x, so we can keep an eye on things. And again, we've got region 1 and region 2. So what's its kinetic energy doing? Well, if we remember from the first part, we used the kinetic energy to find its velocity, and to do that we used the fact that the energy is the integral of f of x dx. Okay, so again we can split this up into the two parts. So for region 1 we have f of x is a constant equals minus 10. Therefore, if we work out the energy, the integral of that, we would simply have that the kinetic energy is equal to minus 10x plus a constant. But we know that this part is linear. Okay, so what about for region 2? here, where we have the linear function of f. So if we were to write that out as an equation, we can use the general equation for a line y equals mx plus c to write the equation for f of x here. So we can see that the gradient of that graph is -1. So we have minus x, and the y-intercept here is minus 10 here. So this means that we can integrate this equation to find an expression for the kinetic energy for this region of the graph, for this region too. Okay, so the kinetic energy here is equal to the integral of -x minus 10 dx. Okay, so if we do that, we find that it is equal to -1/2 x squared minus 10x plus c. Don't forget the plus c. And we can work out what the constant is here by looking at this graph. So we know that from our previous part question here, where we worked out what the energy was at x equals 0, we worked out that the energy was 100 joules. That's this part of the equation here. So we know that kinetic energy equals 100 joules at x equals 0. So if we substitute that in here, we find that c equals 100. So we have our expression for our kinetic energy in region 2, which is -1/2 x squared minus 10x plus 100. Okay, so again, just like the force graph is split into two regions, we have our kinetic energy graph, which needs to be split into these two different regions. So we have a linear region here, and we have a quadratic region here, a negative quadratic. So that's going to have an upside down parabola shape, hopefully drawn a bit better than mine. Okay, so let's sketch this graph. And remember, it's just a sketch, so it doesn't have to be a perfectly accurate work of art here, as long as we get some key shapes and some key points on there. Okay, so what do we have? We have the kinetic energy here in joules, and we have the distance x here, which is in meters. So from x equals 10, which is its starting point, we go from rest, so the kinetic energy is 0, and we have a linear graph that looks a bit like this. And that goes up to this value here. I'm going to write it on here so I don't get in the way of my sketch, of 100 joules, which is what we found in the first part of the question. Okay. And now here we have our upside down parabola shape. So we're going to have a little sort of kink, a little break here, and we're going to have a graph that will go something like this here. Okay. And we can also deduce what the maximum kinetic energy will be. So if we take a look at our force graph here, we know we have 100 joules of energy here. We can see that the force is still acting in the negative direction here. So the force is still going to be creating motion in the negative direction and giving energy to the mass here until the force changes its direction here at a value of x equals -10. So we know that the maximum kinetic energy is going to be at a value of -10 meters. And if we substitute that into our equation here to get our max value, so it's -1/2 times -10 squared minus 10 times -10 plus 100, which is equal to -1/2 times 100, so that's -50 plus 100 here and plus another 100 here, which gives a value of 150 joules for that maximum energy here. And you could also go on to work out what this point here is. You'd end up solving a quadratic equation, but I think this is enough for our sketch for this part question. Okay, so that's what the kinetic energy of this mass in motion looks like. So what does the final part that we're going to have a look at today ask us for? So the next part, we're being asked to sketch its velocity as well as its acceleration as a function of time. So this requires us to think a little bit more here. So the easiest way I find to think about it is to actually look at this force distance graph, think about these two regions, and think about physically what is going on here. What is the motion that this mass is experiencing? So if we remember that our mass had a mass of 1 kilogram, in this region where we have the constant force, so in region 1, where F is minus 10 newtons, we can deduce, using simply F equals ma, that its acceleration must also be minus 10 meters per second squared. Now, what does that remind you of? Well, this, to me, looks like a rounded version of the acceleration due to gravity. And that is exactly how we can think of this region 1 being. We can think of that we're dropping this mass from a height, which would be equivalent to x naught, and it is in free fall towards a surface here at x equals 0. And we have this constant acceleration downwards due to gravity. So what is this region 2? So what happens when it hits the surface? Well, if we think about the movement of the mass here, when the mass hits the surface, we still have this negative force. So the force is still acting in the downwards direction. So the particle is moving downwards, and it's still accelerating downwards, just at a decreasing rate. And once we get to this distance of minus 10 meters here, we can see that the force changes direction. So the force now becomes positive, so it's acting upwards. So now we're starting to slow the particle down, slow the mass down, until we'll eventually bring it to a stop. And we've still got a force acting on it, so it's now going to change its direction, so it's now going to start moving upwards. So what does this remind me of? Well, this reminds me of dropping something on a springy surface, like a trampoline. So we've got spring-like behaviour here, which is also synonymous with simple harmonic motion. So basically what this graph of force, this force distance graph is telling us about is we're dropping a mass of 1 kilogram onto a trampoline. Okay, so with that in mind, we can start to puzzle out what its acceleration and its velocity will look like here. So I'm going to start with its acceleration because I find that easier to start with. You might want to start with its velocity. That's absolutely fine. So let's start thinking about our sketch. So I'm going to try and draw it big because I want to be able to have the velocity graph directly underneath so we can relate the points, the corresponding points in time between the two graphs, which is always good practice if you're asked to sketch two corresponding graphs like this. Okay, so what do we have here? We have the acceleration, which will be meters per second squared, and we have the time, which will be in seconds. Okay, so we're starting from rest, and if you remember, we have our constant force and constant deceleration of minus 10 for the first part. So our acceleration is simply going to be a constant straight line at a value of minus 10. Okay, so now what happens when we hit x is 0? Well, as I said, the force and the acceleration is still in the negative direction, but the amount is decreasing. So our acceleration will be slowly increasing up towards a value of 0. Okay, and that is where we have that the force is 0 here. So that's going to continue increasing now positive as we have our positive force. And if you remember, I liken this to simple harmonic motion. So we're going to have a cosine-like curve. Okay. And this point here, where we have the maximum acceleration, that will be the point where the mass is changing its direction. So we have the maximum acceleration at that point. And it's going to be, we're going to have a symmetrical like shape graph coming the other direction, and we're going to end with that straight line again at the end. So this is a very rough sketch, and that's absolutely fine. But we have these sort of key points here. So we have this point here, where it turns from linear to the curve. We have this point here, where our acceleration is 0. we have this point here where it's at a maximum, and again we have the same corresponding points coming down the other way. So now let's think of its velocity. So it might also help to remember that the acceleration is the second derivative of its distance by time, and the velocity is dx by dt. So essentially, if we integrated this curve, we would find the velocity curve. So we don't have to necessarily do that mathematically, but again, we can qualitatively think about what it's going to look like in relation to these key points that I have marked on here. Okay, so let's have a look at the velocity. So let's draw our sketch. V in meters per second, don't forget your units, and t in seconds here. Okay, so what I'm going to do is I am just going to draw some lines down, some faint lines, so that I can keep track of these corresponding important points on these two graphs. So again, if you're being asked to sketch two graphs with some corresponding important points on them, it's always good to try and lay it out a bit like this. Again, just a sketch, doesn't have to be perfectly neat, but it gets the idea across. Okay, so let's start in this region where we have a constant acceleration. Well, what does that mean? That means that our velocity is going to be linear. If you remember, if we integrate this, we get the velocity. And we're starting from rest, so we're going to start from 0. And we have a negative acceleration, so our velocity is going to be increasing in the negative direction. Okay, so what do we have? In this region here, we have a linear decrease in velocity. And then what? Well, then we can see that our acceleration is increasing, or our negative acceleration is getting smaller, whichever way you want to look at it. And again, we have this sinusoidal-like behavior, which we are used to seeing with simple harmonic motion. So here we're going to have, because we've still got the negative acceleration, our velocity is still going to be increasing in the negative direction, but now it's that curve. So we're going to have something that looks like this. And at the point where the acceleration is 0, we're going to have our maximum or minimum points of our velocity. In this case, it's a maximum negative velocity, or a minimum. Okay, so what now? Well, it's going to come and start curving in the other direction. And we know at this point where the mass is changing direction, it's got its maximum in acceleration, so it's going to have 0 velocity at this point. So it's going to pass through the time axis here. So we're going to have something that looks like this. And again, we've got symmetrical behavior going on here. So we're going to increase to a maximum velocity in this direction. And then we're going to come down in the curve. And then we're going to come down linearly at this point here, where we're back into the region of a constant force. So here we have our velocity time graph, and we can put a few little values on here as well. So we calculated this value here in the first part of the question. So this is the velocity at x equals 0, which we calculated as minus 10 root 2. And we can also, if we wanted to, work out what the maximum and minimum velocities will be based on our calculation for the maximum kinetic energy, which we found in the other part. So we know that the maximum kinetic energy is 150 joules. And so that's equal to a half v squared, with the mass being 1 kilogram, which gives us a value for the velocity of the square root of 300, otherwise known as 10 root 3. So in this case here, it's a minus 10 root 3, and it's going to be symmetrical up here, so we're going to have a maximum of a positive 10 root 3, and this point here where it turns linear again is going to be 10 root 2 here. So here we have our sketch for its acceleration and our sketch for its velocity. So I hope that was helpful going through the first few parts of this long question. Feel free to try the rest of the question yourself. This is just one way that you can go about solving this question. You might find it easier to go through other ways. This is the way I prefer. So I hope this was helpful, and we will see you again next week for another PAT Problems video.